Welcome back. In the previous video, we have come across these notions. So we started with a bounded function on a closed interval, bounded real valued function. We introduced the notion of partitions of an interval, and for a given partition, we had introduced the notion of LPFs and UPFs, and we are now in a better shape to go forward towards finally defining the notion of Riemann integration. First, we are going to give you a lower bound for the quantity LPF and an upper bound for the quantity UPF. So it always turns out that LPF is bigger than or equal to small mf times b minus a, whereas UPF is always less than or equal to big mf times b minus a. The proofs of these assertions are quite easy and simple. I will only give you a sketch of the proof for the first part and will leave the second part, second inequality, as an exercise for you to prove. How do we prove this? We have already observed that MF is less than or equal to MIF. This holds true for all I equal to 1 to n. I multiply each of this, both sides, by the quantity xi minus 1. So the inequality still persists. I take sum of these quantities as I varies from 1 to n. We get this inequality. Now MF does not depend on I, so it comes out of the summation, and on the left hand side we are left with the sum of all the quantities which are like xi minus 1. Now as we sum up these quantities, it is easy to see that sum I equal to 1 to n, xi minus 1 is equal to b minus a, and this gives us the proof of the assertion. As I said, I leave the upper bound for UPF as an exercise. Now let me formally define what do we mean by refinement of a partition. So let us start with a partition P of the interval AB. We say that another partition P star is a refinement of the partition P if P is a subset of P star. Now we prove our first assertion related to refinement of partitions. It has two parts. So it says that if f is a bounded real valued function on a closed interval AB, and if P and P star are partitions of AB such that P star is a refinement of P, then we have the following inequalities. LPF is less than or equal to LP star F, and UP star F is less than or equal to UPF. So again, the proofs are quite similar, and so I will give you a sketch of the first part and I will leave the proof of the second part as an exercise. I hope that you guys will do this exercise. That will make you comfortable with this kind of notations. So we want to prove that LPF is less than or equal to LP star F. Let us see what are the key ideas. The full proof is given here, which you can read from the slides. I will upload the slides during the class. So let's see what are the ideas. So first, our claim is that it is enough to prove the assertion in the case when P star contains exactly one more point than P. Once you have shown this, you could go inductively to prove the general case. Now we will always assume that we are in this situation, that P star contains exactly one more point than P, and let us see how the partitions look like. So suppose that this is our interval, closed interval AB, and we have this points x1, x2, and the extra point of P star, let me call it y. So in particular, P star is, let's say, y union P. The point y should somewhere be caught between xi minus 1 and xi for some value of I. So let me say that this is our y. So for corresponding to the partition P, we have this quantities MIF, and we also have xi minus 1, which will give us uh, the quantity LPF, which will contribute towards LPF. And when we consider LP star F, you will see that the only difference comes here in this interval. So if you grant me to call the infimum of fx in the smaller interval xi minus 1 to y, so I divide this interval, subinterval, into two parts, of course, and this will be yxi. And suppose that I call mi prime f to be the infimum of fx as x varies in this interval, and mi double prime f to be the infimum of fx as x varies inside this interval. So for LP star f, instead of this term MIF, we will have this term. So what is the corresponding term here? Mi prime f times y minus xi minus 1 plus mi double prime f times xi minus y. Note that we have already used such kind of arguments before. Note that xi minus 1 comma y is contained inside the interval xi minus 1 xi. What does it mean? It simply means that mi of f is less than or equal to mi prime f. Similarly for this, the interval y comma xi is contained inside the bigger interval, the ith subinterval of P, and consequently we also note that mi double prime f, this is also bigger than or equal to mif. Now if you do some simple algebra with the expansion of LPF, you will see that we will get this inequality. The assertion corresponding to UP star F and UPF is proved analogously, and as I said, it is left as an exercise. Claim 2, it says that if P1 and P2 are any two partitions of AB, then, and if f is a real valued bounded function on the closed interval AB, then LP1F is less than or equal to UP2F. How do we prove this? This is very easy to prove. You just take a common refinement which is given by P1 union P2, and you apply the previously known results that we have already proved or left as exercises. So since P star is a refinement of P1, we get from our previous claim that LP1F is less than or equal to LP star F. This follows from claim 1. This also follows from claim 1. This was left as an exercise, if you remember, and we have seen this, that for any partition P we have this inequality in my previous video. Now let me just not forget our geometric intuitions yet, and let me tell you very quickly what do these things mean geometrically. So the claim 1 is the following. It says that LPF is less than or equal to LP star F. So this was geometrically area of a network of a smaller rectangle, area of let's say a smaller area of network of a smaller rectangle, of area of network of smaller rectangles, and so this was corresponding to P. So as we have seen in our first video that as we keep on making the partitions smaller, or we keep on introducing more points in the partition, this the area of the network of smaller rectangles increases. So exactly this is going to exactly captured in this inequality. So here P star was a partition of P, and since we have introduced more points, we have a better approximation of the area from below, so to speak. Similarly, we can make sense of the inequality that UP star F is less than or equal to UPF. So uh, from above, if we keep on introducing more points to the partition, then we get better and better approximation of the area. So this information, this geometric information are captured in these two inequalities. Now what does this say? What does this claim 2 say? Claim 2 says that LP1F is always less than or equal to UP2F. But this is really speaking a reality check. What do I mean by that? So this is area of area of the network of a smaller rectangles, and this is area of the network of bigger rectangles. So we always expect that irrespective of whatever partition that you take, the area of the network of smaller rectangles will always be less than or equal to the area of the network of bigger rectangles. So these are very intuitive facts in terms of geometry and in terms of the notion of area, but here we have just made it very concrete and proved it mathematically. Next, we have these two sets. The first set, let me call it L for the purpose of this video, and U, this set, for the purpose of this video. What is L? L consists of the set of all LPF. F is fixed, but let us vary P over the set of all partitions of the closed interval AB. UPF, again F is fixed, and let us vary P over the set of all partitions of the closed interval AB. Now we have seen that the set L is bounded above. What do I mean by that? We have already observed that LPF is less than or equal to big MF times B minus A. Similarly, we have, so this is true for all partitions P. Similarly, we have also noticed that UPF is always bounded below by small mf times B minus A. So UPF is always bounded below by small mf times B minus A. Now, once we have a set of real numbers which is bounded above, after reading so much calculus that you have done so far, it is by second nature of you that you will ask for the supremum of the set. So let us talk about the supremum of this set which is bounded above. So let me call this number LF. It is the supremum of L, and let me also call UF to be the infimum of this set. Note that these two quantities do not anymore depend on any partitions. We have taken partitions and we have refined them, or we have taken the set of all partitions, we have considered the set of all LPFs, taken supremum, we have considered the set of all UPFs and taken infimum. So now you might be expecting that this LF would still be less than or equal to UF. Indeed, this is the case, and the proof is very easy, and the technique that we are going to use for this proof is very common in calculus and real analysis as well. What do? We take a partition of our choice Q of the interval AB. We have already seen by claim 2 that LPF is less than or equal to UQF for each of the partition P. Now we take supremum of all the LPFs, we will see that this is less than or equal to UQF. And what is this supremum? The supremum is exactly equal to the quantity LF by definition. But now the inequality that we get here does not really depend on Q. It is going to be true for any partition. Remember, when you chose this partition Q, you did not impose any condition on that partition. So this inequality is going to be true for all partitions Q of AB. We can now take infimum of all the values of UQF as Q varies over the set of all partitions of AB, and we have just proved that LF is less than or equal to UF because this quantity is same as UF. Now I think you might be wondering what is the relation between this inequality and the integration of fx, the definite integration of fx. So this quantity that we are interested in, and many of you might have guessed correctly that this should lie somewhere between LF and UF. And if you recall the information that was given in our first lecture, you might be thinking that we are really very close to define the notion of integrability. Indeed, that is the case. We are finally at a stage of defining the notion of Riemann integrable functions. So here is a typo. Let me fix that. So a function, a bounded real valued function on a closed interval AB is said to be Riemann integrable if LF is equal to UF. So LF is equal to UF. Of course, in this case, if LF is equal to UF, then it must so happen that integral fx must take the same value that LF and UF take. So truly this is the case. Integral of fx, if f is integrable, then integral of fx as x varies from a to b is defined to be the common value that is taken by LF and UF. Let me give you the first example, which is a very trivial one. So let us fix an interval, a closed interval AB, and a real valued bounded function, and the function is a constant function which is of course bounded. So C is a real number. So fx takes the value C for all x inside the closed interval. Now you can consider any partition of your choice, and whatever I am going to say here below will not change. Fix any partition and take the ith subinterval. You see that the function f is constant inside the whole interval, and consequently for all x, as x varies inside this ith subinterval, let me be a bit fancy and write like this. As x varies inside this ith subinterval, the values of value that f will take will always be equal to C, and consequently what we will have is that the supremum of all the values that f takes in when x varies in the subinterval is given by C, as well as the infimum of all the values that f takes in the subinterval xi minus 1 xi is also equal to C. Now we just have to write down the sum. LPF is always given by C times xi minus 1, and this C is constant, and this sum, as we have seen before, is equal to B minus A. So LPF is equal to C times B minus A. You can also see by exactly the same computation that UPF is also equal to C times B minus A. What is more important, I have already said this, that this calculation that we have made just now holds true for all possible partitions of the closed interval AB. What does it tell us? It tells us that LF, if we take supremum of all LPFs, we get C times B minus A. Also UF, if we take the infimum of all UPFs, that is also equal to C times B minus A. Consequently, f is integrable. This is by the definition of integrability, and what is the integral? It is the common value that LF and UF takes. You may be wondering, are all the functions that one can think of integrable? The answer, of course, is no. Here is a counter example. This example is called the Dirichlet function. So fx, f is a function which is defined on the closed interval 0 1, and fx takes value 1 at every rational point inside the closed interval 0 1, and 0 at every irrational point inside the closed interval 0 1. Now the key idea of working with this example is the following, that between any two real numbers, you can choose any two real numbers, there will be a rational number in between them and an irrational number in between them. So you take any partition of the closed interval 0 1 and you consider the ith subinterval, then there will be, let me write with different colors, there will be a rational number and there will be an irrational number, let me call it z. So what will be the supremum of all fx inside this subinterval? This will be a big MIF, that is always going to be 1 because there is a rational number. So big MIF is going to be 1. And also what will be the small MIF? The small MIF is going to be 0 because there is an irrational number inside this interval. Again, this is true for every partition that you can think of. What is UPF? UPF is sum of all big MIFs times xi minus 1. So MIF is equal to 1 here, as we have seen, and consequently we will be left with summation I equal to 1 to n xi minus 1, and so this turns out to be equal to xn minus x0, as we have seen, which is equal to 1 minus 0, which is equal to 1 eventually, and also UPF is going to be 0. Now this calculation of LPF and UPF, as I have mentioned many a times, that will remain the same in this example independent of whatever partition that you can choose. This gives us that UF is equal to 1 and LF is equal to 0. What does that tell us? That tells us that f is not integrable. So we have defined the notion of Riemann integrability. We have seen we have seen an example of a Riemann integrable function, and also we have seen a non-example of a Riemann integrable function. In the next lecture video, we will work out more properties of Riemann integration. We will come across more examples of this notion. Till then, goodbye.